Hello everyone, and welcome to our lesson on arrays. Today we will learn about one of the most fundamental data structures in computer science and programming. Arrays are like organized storage containers that help us keep our data in a structured way in computer memory. Whether you are working with Python, Java, C++, JavaScript, or any other programming language, understanding arrays is essential. We will start slowly and build your knowledge step by step, making sure everything is clear and easy to understand. By the end of this lesson, you will know exactly how arrays work, how they store data in memory, and why they are so important for efficient programming. Let's begin our journey into the world of arrays and see how they can make your code more organized and efficient. Now let's understand what an array actually is. An array is a collection of elements that are stored in consecutive memory locations. This means all the data items are placed right next to each other in your computer's memory. Each element in an array can be accessed using something called an index number. Think of the index as an address that tells you exactly where to find each piece of data. To make this easier to understand, let's use a real-world example. Imagine an array is like an apartment building. Each floor of the building has a specific floor number, and each floor contains something, maybe an apartment or an office. In the same way, an array has numbered positions called indexes, and each position contains a piece of data. When you want to find something in the apartment building, you use the floor number. When you want to find data in an array, you use the index number. This simple concept of organizing data with numbers makes arrays incredibly useful for storing and accessing information quickly in your programming projects. Now, let's see how arrays actually look in computer memory. Let's declare an integer array, int data with 5 elements, containing the values 10, 20, 30, 40, and 50. Here we can see a visual representation of this array stored in memory. Each orange box represents one memory location where we can store data. Notice how all these memory locations are placed right next to each other. This is what we mean when we say arrays store elements in consecutive memory locations. Let's look at the data inside each box. We have the numbers 10, 20, 30, 40, and 50 stored in our array. Now, look at the numbers below each box. These are the index numbers, 0, 1, 2, 3, and 4. This is very important to remember. Array indexing starts from 0, not 1. So the first element is at index 0, the second element is at index 1, and so on. If we want to access the value 30, we would use index 2. If we want to access the value 50, we would use index 4. This layout in memory makes arrays very efficient because the computer can quickly calculate where any element is located just by using simple math with the index number. This is why arrays are so fast for accessing data in programming applications. Now let's dive deeper into what contiguous memory locations actually means at the technical level. Here we have an array declaration, int numbers with 4 elements containing the values 10, 20, 30, and 40. When we say arrays use contiguous memory, we mean there are no gaps between the elements in memory. Let's see exactly how this works. Each integer in most systems takes 4 bytes of memory. Look at the memory addresses shown in red below each element. The first element at index 0 is stored at memory address 1000. The second element at index 1 is at address 1004. The third element at index 2 is at 1008, and the fourth element at index 3 is at 1012. Notice the pattern. Each address increases by exactly 4 bytes, which is the size of one integer. There are no gaps or unused bytes between our array elements. This contiguous layout is what makes array access so incredibly fast. The computer uses a simple mathematical formula to find any element. The formula is memory address equals start address plus index multiplied by element size. For example, to find element at index 2, we calculate 1000 plus 2 times 4 equals 1008. The computer jumps directly to address 1008 and retrieves the value 30. This direct calculation works because the elements are stored contiguously with no gaps. If there were gaps or if elements were scattered randomly in memory, this simple formula would not work, and accessing elements would be much slower. This is why we emphasize that arrays store elements in contiguous memory locations. It is this fundamental property that gives arrays their speed and efficiency in programming. Now let's learn about the basic operations we can perform with arrays. First, let's declare an array, int data with 5 elements, containing the values 5, 10, 15, 20, and 25. There are 4 fundamental operations that you will use most often when working with arrays in your programming projects. First, we have access element. This means getting a value from a specific position in the array. For example, if we write data at index 2, we get the value 15. This operation is very fast because we can directly jump to any position using the index. Second, we have update element. This allows us to change the value at a specific position. For example, data at index 2 equals 35 means we are changing the value from 15 to 35. This is also very fast. Third, we have find length. This tells us how many elements are currently in the array. In most programming languages, we use something like data.length, which returns 5 in our example. Fourth, we have loop through. This means going through each element in the array one by one. We often use for loops to visit every element in the data array and do something with each value. These 4 operations are the building blocks of working with arrays. You will use them constantly when developing applications in any programming language, whether you are storing user data, managing lists, or processing information. Understanding these operations well will make you a more efficient programmer. Understanding time complexity is very important when building efficient applications. Let's see how fast different array operations are. Consider this example. Int values with 100 elements, containing the numbers 1, 2, 3, all the way up to 100. Some array operations are extremely fast. We call these constant time operations, or big O of 1 operations. The fast operations include accessing an element by index, like values at index 50. This is fast because the computer can directly jump to that memory location using simple math. Updating an element by index is also fast, like setting values at index 50 equals 999. Again, we know exactly where to go in memory. Getting the array length using values.length is also very fast because this information is usually stored with the array. However, some operations are much slower. These are called linear time operations, or big O of n operations, where n is the number of elements in the array. Searching for a value is slower because we might need to check every single element until we find what we are looking for. For example, finding where the value 75 is stored might require looking through the entire array. Inserting a new element in the middle of an array is also slow because we need to move all the elements after that position to make space. Similarly, deleting an element from the middle is slow because we need to move all the remaining elements to fill the gap. When developing applications in any programming language, choosing the right operations can make your programs much faster and more responsive for your users. Now let's see exactly how array element access works step by step. First, let's declare our array, string fruits with 5 elements containing apple, banana, cherry, date, and pear. Here we have our fruits array visualized with 5 elements. Each element has an index number below it, 0, 1, 2, 3, and 4. Let's say we want to access the element at index 2 using the code fruits at index 2. We want to understand exactly how the computer finds this element so quickly. The computer doesn't need to check each element one by one. Instead, it uses a mathematical formula to jump directly to the correct location. Let's see this process in action in the next slide. Perfect. Now we can see exactly what happened. The computer used the index number 2 to calculate the exact memory location where the element is stored. Notice how the element at index 2 is now highlighted in bright yellow, and the text cherry is shown in red to indicate it has been found. Look at the memory addresses shown below each element. The first element, apple, is at address 2000, banana is at 2008, and cherry is at address 2016, highlighted in red. The computer did not need to check apple at address 2000 or banana at address 2008. It jumped directly to address 2016 and found cherry immediately. Let me explain the mathematical formula the computer used. The formula is address equals start address plus index multiplied by element size. In our example, 2016 equals 2000 plus 2 times 8. Let me break this down. 2000 is our starting address, 2 is the index we want to access, and 8 is the size of each string element in bytes. So, 2000 plus 16 equals 2016. This is why we say array access is in big O of one operation or constant time. No matter how big the array is, whether it has 5 elements or 5,000 elements, accessing any element by its index takes the same amount of time. This direct access using the mathematical formula is what makes arrays so powerful and efficient for programming applications. When you need to quickly find specific data in your programs, arrays provide lightning-fast access. Now let's see how we can update or change elements in an array. Let's declare an integer array, int grades with 4 elements, containing the test scores 85, 92, 78, and 88. Here we have a student grades array with 4 test scores. Let's say we need to update the grade at index 2. Currently it shows 78, but we want to change it to 95 because the student retook the test and got a better score. We use the code, grades at index 2 equals 95. This tells the computer to go to index 2 in the grades array and replace the old value with the new value of 95. Let's see what happens next. Excellent. The update operation is now complete. Notice how our array declaration now shows the updated values, int grades with elements 85, 92, 95, and 88. The value at index 2 has changed from 78 to 95. Look at the visual representation. The element at index 2 is now highlighted in bright yellow, and the value shows 95 in red text. Look at the memory addresses shown below each element. The first grade 85 is at address 3000, the second grade 92 is at 3004, and the updated grade 95 is at address 3008. Let me explain how the computer performed this update using the same mathematical formula. The formula is address equals start address plus index multiplied by element size. In our example, 3008 equals 3000 plus 2 times 4. Here, 3000 is our starting address, 2 is the index we want to update, and 4 is the size of each integer in bytes. So, 3000 plus 8 equals 3008. The computer went directly to address 3008, just like in the access operation, and replaced the old value 78 with the new value 95. This update operation is also very fast, taking constant time or big O of 1. The computer doesn't need to search through the array or move other elements around. It simply goes to the exact memory location and changes the value. This is another reason why arrays are so efficient for programming applications. Whether you need to update user preferences, modify game scores, or change any stored data, array updates happen instantly. In your programs built with any programming language, you will use this update operation frequently to keep your data current and responsive to user interactions. The combination of fast access and fast updates makes arrays perfect for storing data that needs to be frequently read and modified. Congratulations! You have successfully completed the Complete Arrays tutorial. You now understand that arrays store data in consecutive memory locations, which makes them incredibly efficient for organizing related information. You learned that array indexing starts from 0, not 1, which is fundamental to working with arrays in any programming language. You discovered that accessing array elements is in big O of one constant time operation, meaning it's super fast regardless of how big your array is. You saw that updating array elements is also O of one constant time, making changes to your data instant and efficient. You understand that searching for values in arrays takes big O of n linear time, which depends on the size of your array. Most importantly, you now know why arrays are perfect for programming and data storage management. You have seen step-by-step examples of how computers access and update array elements, giving you a deep understanding of how these operations work behind the scenes. Thank you for learning with us today. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you, and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.